Hello everyone, this is Dr. Hopkins, narrating the next in our series of videos for 472. In this video, we're going to describe the steady state approximation. So recall from the last video, we ended with this idea of this mechanism of consecutive reactions where you have reversibility in the first step. And we had, so A plus B, giving us some intermediate. And then we had set up our rate of appearance of product and intermediate as such. And then we described in that video the pre-equilibrium case where if K minus 1, so this reverse reaction, is much faster than the product forming reaction, then this is allowed to come, this first kind of steps are allowed to come to equilibrium. So what happens if the second step, this product forming reaction, is much faster than that? Then this first step is basically rate limiting. So in other words, we're almost like our consecutive first order reactions where we ignore the reverse reaction. But in that case, our formation of product is just due to K1A times B, or our second order standard reaction. So what do we do if there isn't a rate limiting reaction in K1, K minus 1, and K2? What if they're all relatively similar? Or we don't have a pre-equilibrium? So that's when we evoke what we call the steady state approximation. And then basically what we're going to do is we're going to say that the concentration of the intermediate is going to not change over a large time period of the reaction. And that allows us to take this derivative of the concentration of I with T and set it equal to 0. So if it's not changing, we have a rate of 0. And then if we use our expression from the previous page where we derived how we get to the differential of the intermediate concentration, we have this. And if we rearrange this, we can, since it's equal to 0, set this on both sides, and then we can solve for I, our intermediate concentration, which if we have in our product formation, if it's K2I, remember the intermediates can't end up in the rate law. So if we substitute our steady state approximation assumption into the I, we get this ratio of rate constants and then first order in A and B in terms of our product formation. So let's do a short example. So we'll have this is our expression, this is the stoichiometry of the reaction. We're going to have two NOs plus O2. We're going to generate NO2. The proposed mechanism is that we have a reversible first step. So we're going to put K1 and K minus 1 on the forward and the reverse reactions. And then the second step is we're going to add in O2. So it's a little different than our example to react with the product of the first step to generate our products. So we're going to write this mechanism or figure out what this mechanism would be if we assume the steady state approximation. So the process is, let's identify any intermediates in our reaction. And so we'll look, NO is a reactant, O2 is a reactant, NO2 is a product. The only thing that doesn't show up in our stoichiometry is the N2O2. And we're creating it and destroying it. So that's an intermediate in the process. And then we want to write out a steady state approximation rate expression for all of our intermediates. In this case, we only have one. It's the N2O2. And so we know we create it with this first step, K1, and that's a bimolecular process, so second order in terms of NO. And then it can reversibly fall back apart into the two NOs, so that's K minus 1 times the N2O2 concentration. And then it can also react away, so minus K2 with oxygen to form our product. And then we set that equal to 0 because we're saying that the concentration of this is going to stay constant over time. And then we're going to write out what would be our rate law expression from this mechanism. And in terms of the production of the product or appearance of the product, we would write it here. We have the 1/2 in terms of our stoichiometry of the NO2. So the rate of appearance is in the second step is the only place the product appears. So it's K2 and first order in N2O2 and O2. And then we're going to take sorry, we're going to take this steady state approximation, so we have this equal to 0, and we're going to, we need to substitute in our formation of product differential for N2O2, so we use the steady state approximation to get a value of N2O2, and it's this ratio where we have second order in NO, and then we have a minus 1 order of O2 in this case. And so then we write out, here's our rate of appearance of product, and we substitute in our N2O2 into our original rate of appearance of product, and we end up, so it was N2O2 times O2, so here is the expression from N2O2, and then the first order in O2, and this is what we would predict based on the steady state approximation that the rate law of this reaction would be. So we would predict it would be second order in NO, first order in O2, although these would then cancel if we, although it's K2, they wouldn't exactly cancel. So we would get a little bit more of a complex rate law. So how do we know if this is the correct rate law? This is what the steady state approximation predicts. And this is where we rely on experiment. So kinetics is a kind of experimental science. So we're going to compare to the experimentally determined rate law. Now, in this case, the experimentally determined rate law is that the overall rate of appearance of the product, or the rate law of the reaction, is some rate constant that's an experimentally determined rate constant. It's second order in NO and first order in O2. And clearly this does not match that particular rate law, right? So we have this denominator here that's not working in terms of this. So is there some way we could change how we interpret the proposed mechanism on the previous slide to match this experimental rate law? And I will leave that for another time.